Hey everybody, it's Miss Berry, and in today's video we're going to start chapter 10, which is called hypothesis testing. Um, and today's video is just going to be over section 10.1, which is the fundamentals of hypothesis testing. You're not going to need your calculator today. We are just learning the basics of what a hypothesis test is and learning the structure and how you will conduct your hypothesis test. Okay, so this is one of my favorite topics to cover because this is something that you very well may do again if you go on and you take another stats class, or if you do research after you finish your degree, or if you go on to graduate school and you're doing some kind of research, then you will definitely do a hypothesis test again in the future. Um, Hypothesis tests really aren't terribly complicated, although I think they have a bad reputation for being complicated. But they're really just broken down into these 4 steps. The first step is to state the null and alternative hypotheses. We're going to talk more about what the null and alternative hypotheses are, but just in general, just know that the null hypothesis is the value that you currently believe to be true, and the alternative hypothesis is what you would like to prove. All right, so null hypothesis, what's currently believed to be true, and your alternative hypothesis, this is what you want to prove. All right, so one example is maybe you're doing research with like the Jekyll Island Sea Turtle Center, and you keep seeing that the average size of, maybe the average diameter of the sea turtle shell is supposed to be a certain length, and maybe you keep seeing that these turtles are actually smaller than that average length. So your null hypothesis would be the currently believed, average diameter of a sea turtle, and then your alternative hypothesis could be like what you think is true. So maybe it's less than average, or maybe it's greater than average. All right, the next step in our hypothesis test is to determine what type of test should be used, and then we're supposed to state the significance level, which is called alpha. All right, so I have a little table to help you figure out which test to use. And just to give you a little quick overview, this is the Greek letter alpha. It's a lowercase alpha. And this is going to be given to you in the problem. Given in the problem. If you were doing real research in real life, how would you determine your alpha level? You would just look at prior research in your field. They use like traditional alpha levels for certain fields. Certain fields may use larger alpha levels, certain fields may use lower alpha levels. Just to give you the interpretation of what alpha is, it is the probability of making a type 1 error, which we will talk more about later. Right, but you can think of it as the probability of making a mistake, right? So you would like that to be low, right? So you don't want to make a mistake whenever you're doing these tests, especially if you think about if you're doing research in like health sciences, if you're doing research in like pharmacology, testing out new medications, you want to make sure that you have as accurate results as possible. So you would like to minimize the chance of making a mistake. All right, the third step is what would take you the longest in real life. This is where you would gather your data and then calculate your necessary sample statistics and then generate your graphs, make frequency tables, all that kind of stuff. So in real life, this might take you months, it might take you years. So imagine if you're doing like cancer research, that might take you years to gather all that data to see how effective a treatment was in preventing like the recurrence of cancer. All right, so this in real life would take you, in a lot of cases, a significant amount of time. And then lastly, you will draw your conclusion based on the chosen method. So you can use what's called a rejection region method or a p-value method. Typically in the social sciences, they like to use the rejection region method, and then in STEM fields, they use the p-value method. So again, we have what's called a rejection region method. And then p-value method. And the social sciences, that also extends to education. So social sciences, think like sociology, psychology, education, they like to use this rejection region method. But in the STEM fields, they typically use what we call a p-value method. And to me, that one's a lot easier to use. P-values can be hard to interpret, but the actual execution of the method is pretty simple. All right, and then the last thing you'll do is just interpret your decision, and I have some little template sentences for you to copy down later on. So you'll see that in just a few minutes. All right, so let's start by talking about each one of the steps. We said our first step was to write the null and alternative hypotheses. So we have symbols for each of these, and depending on what class you're in, they may use a different symbol. They almost always will use H with a little 0 here for the null hypothesis. HO is what we call that. HO. And then for our alternative hypothesis, we're going to use HA, but other textbooks use H1. All right, so you could also see H1 used to describe the alternative hypothesis. All right, so a couple of things to know about the null hypothesis. This is the value that is currently believed to be true, and in an ideal scenario, you would be able to disprove this null hypothesis. You would have enough evidence to say that that null hypothesis is incorrect. And since the null hypothesis is the value that is currently believed to be true, it is always a statement of equality. That means it's going to have an equal sign. So here, a statement of equality means equal sign. Whoa, sorry. Try that again. Equal sign. Okay. Now, our alternative hypothesis, this is going to be determined by what we're trying to prove. So again, if we were looking at like the turtle shell example, we might believe that the turtle shell is larger than what's currently believed. We might think it's smaller than what's currently believed, or we just might want to say, I don't know if it's bigger, if it's smaller. I just think it's not this number. All right, and just like how the null hypothesis was always a statement of equality, the alternative hypothesis is always a statement of inequality. And so our options here are going to be less than, greater than, or not equal to. So you, just depending on the scenario of your problem, you might have a less than in your alternative hypothesis, you might have a greater than, or you might have a not equal to. Right, so if you struggle with these, make sure you write these down. That first one is less than. Second one is greater than. And then, of course, the last one is not equal to. Okay. All right, so here we are just going to practice setting up some null and alternative hypotheses. It says, based on past sales, a shoe manufacturer considers the mean size of women's shoes to be 7.5. The manufacturer would like to test if this is still the case. All right, so a couple things that are jumping out to me here. Seeing the word mean. All right, so I know that this is involving the population mean, which the symbol for that is mu. All right, I see that the value that's currently believed to be true is 7.5. And the manufacturer wants to test if this is still true. He doesn't seem to have an idea one way or the other if women's shoes are the mean size is larger or if it's smaller. He's just trying to test if this claim is still true. All right, so first thing you're going to do is just set up your null and alternative hypotheses, HO and HA. Since we're doing a mean, we're going to go ahead and put mu in each one. we said that the null hypothesis always includes a statement of equality, so put it equal to in there. And this is the value that's currently believed to be true. So we currently believe that the average women's shoe size is 7.5. The manufacturer would like to test if this is still true. He's not saying that he thinks women's shoes are greater on average than 7.5 or that they're less than 7.5 on average. He's just wondering, is it still 7.5? So since he's not leaning one way or the other, we just use a not equal to for our alternative hypothesis. If you use a not equal to in your alternative hypothesis, so if you use not equal to in HA, this is called a two-tailed test. All right, so what does that mean for you? That means that if you're looking on your little normal distribution, and then your mean 7.5 is right there in the middle, they're going to look on both ends of the normal distribution. All right, so we're splitting our alpha level, which is our level of significance, we're splitting that up between the two tails. Okay, let's look at another example. Here we have a sports analyst is testing her claim that the mean weight of this year's NFL lineman is less than in past years. Assume that over the past 5 years, the mean weight of NFL linemen was 320 pounds. All right, so again, we're seeing the word mean. This sports analyst believes that NFL linemen are weighing less than they did in the past, and the value that's currently believed to be true for their weight is 320 pounds. All right, so go in here and write HO, HA. We saw the word mean, so we'll go ahead and put mu in each one of these statements. All right, we know that the null hypothesis HO always gets the equal to. Find my cursor. Oh, there, way over there, okay? And the value that's currently believed to be true is 320 pounds. That's what we're believing for their current average weight. And this analyst believes that linemen now weigh less than that. So we're going to do the mean weight is less than 320. All right, so mean weight is less than 320. All right, one more. A nationwide study shows that children watch a mean of 3 hours of TV per day. A mother in Louisiana believes that this is an underestimate for children in her area. She conducts a local survey to test her belief. All right, so once again, I see the word mean, the value that's currently believed to be true. We're thinking that children watch about 3 hours of TV every day. And this mother believes that this is an underestimate. So she believes that this is actually lower than what children actually watch. So she thinks that children watch more than 3 hours a day. She believes children watch more than 3 hours per day. All right, so given that information, let's write our null hypothesis and our alternative hypothesis. We saw the word mean, so we'll go ahead and put mu in there. Null hypothesis always gets the equal to. The value that's currently believed to be true is 3 hours a day, so mu is 3. And this mother believes that children actually watch more than 3 hours a day, so we're saying that the mean is greater than 3 hours a day, so greater than 3. All right, so how do we know which test to use? If you are doing a hypothesis test for a mean and your population standard deviation is known, we talked about this back when we were talking about confidence intervals, but this is a pretty rare scenario, but it does happen. If you are in this situation, you would do something called a z-test. All right, so if you were in this situation where you were doing a hypothesis test for a mean, and your population standard deviation was known, you would do a t-test, or excuse me, a z-test. Speaking of t-test, if you're doing a hypothesis test for a mean and your population standard deviation is unknown, that's when you do a t-test. So that's when you do a t-test. And then lastly, we're going to look at, just so you have some exposure to these last type of hypothesis tests, we're going to show you, or I'm going to show you how to do a hypothesis test for a population proportion. And this is called a one, in our calculators, it's called a one proportion Z test. One proportion Z test. All right, so those are the functions in the calculator that you'll use to do those. Now, how do you get there? You're going to click on the Stat button. If you have your calculator handy, you could check this, but if not, it's okay. We'll go through it in the next section. So you would click on the Stat button, and of course that little edit screen would come up. You would go over to the right, and you would go to Test. You would have to go over to the right twice. That's the same place where we found our confidence interval options, Z interval, T interval, and they would be right there at the top. So Z test, T test, and one proportion Z test should be all near the top. All right, so how do we choose our level of significance, which again is called alpha? Level of significance is called alpha. Alpha is the probability of making what we call a type 1 error. We'll get into that later. But you can think of it as like this is the chance of making a mistake. All right, so you want your alpha level to be low, right? Because you don't want to make a mistake. But again, if you have it too low, then you almost never can disprove your null hypothesis. So you have to find a balance between picking a low alpha level so that you are running a low risk of making a mistake, but also being able to find statistically significant results. All right, so what do we mean by statistically significant? This is a common goal of statisticians. We would like to find statistically significant results. That means that you are able to what we call reject the null hypothesis. This helps us quantify whether the result is due to chance or if you are actually finding out brand new information that hasn't been discovered before. Whenever your finding is significant, that means that you can feel confident that the result is real and not that you just got lucky and you got a good sample. Right, so the value of alpha is directly related to your chosen confidence level, and so is its interpretation. So again, if you remember our interpretation of confidence level, if we said like we are 95% confident that the true population mean is between two values, we had a 5% chance that we were making a mistake. And so that is the interpretation of alpha. Right, so alpha is our chance of making a mistake. All right, so again, the next step, and this would really take the longest in real life, would be to gather the data and then calculate the necessary sample statistics. But in our case, it's just going to be given to us. And next, you are drawing a conclusion and then interpreting your decision. There's only two possible outcomes for a hypothesis test. You could either reject the null hypothesis, that's what you would like to do. So this is sort of your ideal outcome. Doesn't always work out, but this was what you would like to happen. You would like to reject the null hypothesis. That means that you had enough evidence to disprove the value that was currently believed to be true. All right, so you had enough evidence, enough solid evidence that you were able to disprove that value, that null hypothesis that was currently believed to be true, which is what you wanted to happen. Now, often in real life, you do not have enough evidence to prove what you would like to prove, and so you have to do what we call fail to reject the null hypothesis, and that again just means that you did not have enough evidence to disprove the value that is currently believed to be true. All right, so very often you have to fail to reject the null hypothesis in real life. It's actually pretty rare that you get statistically significant results and that you are able to reject the null hypothesis. Right, so if you're doing your own research, you're going to fail to reject the null hypothesis pretty often. Now, for the stuff that we're going to do in class, obviously all of these problems are constructed in such a way that we will be able to see both types of outcomes. So you'll see some reject, some fail to reject, but in real life, like I said, you often have to fail to reject. All right, so there's a really easy way to remember which conclusion that you're going to draw, and it's based on something called a p-value. So if you're in like the social sciences, a lot of times they want to do what's called a rejection region method. Right, so you might, if you take another stats class, they might use the rejection region method. And so the way that this works is, let's just imagine we're doing a two-tailed test. So you would have some critical value, we'll call it negative C for negative critical value, and some positive critical value. And the tails would be your rejection region for a two-tailed test. And you calculate your, what we call your sample statistic. And if it fell into either one of these regions, then you would reject the null hypothesis. If it fell somewhere in between here, so if it was somewhere in between these two numbers, you would fail to reject. Now, to me, this is not the easier way to do hypothesis tests, so that's not the way I'm going to teach you. I'm going to teach you the p-value method, which in my opinion is much easier. And here is the easy way to remember which conclusion to draw. It says if p is low, reject HO. Right, so what does that mean? That means if your p-value, which is something that your calculator will tell you, so if your p-value is less than your alpha level, you reject HO. If your p-value is greater than your alpha level, or if it's equal to your alpha level, so that's supposed to be a greater than or equal to. Let me try that again. Greater than or equal to alpha, you fail to reject HO. Every once in a while, you'll get a situation where when you round your p-value, it ends up being exactly the same as your alpha. You have to fail to reject the null hypothesis in that scenario. All right, but the way to remember this is if p is low, reject HO. So if p is lower than alpha, you reject HO. If it's not lower than alpha, so if it's bigger than alpha or if it's equal to alpha, then you're going to fail to reject HO. All right, and then our last slide here is our template for our conclusion statement. So just write these down. This will help you when you are interpreting the results of your hypothesis test. We have two templates here, one if you reject, one if you fail to reject. So the first one says, if you reject the null hypothesis, this is the sentence you're going to use. There is sufficient evidence at the blank level of significance. That's where you put alpha. All right, so that's where alpha goes. You would say 0.05 or 0.01 or whatever alpha was. So there is sufficient evidence at the blank level of significance that blank. So that blank on the end, that's going to be sort of a rewording of your alternative hypothesis. All right, so that last blank is a rewording of your hypothesis, of your alternative hypothesis. All right, so for the shoe size example, you might say there is sufficient evidence at the 0.05 level of significance that women's shoe size, the mean women's shoe size is not 7.5. All right, so you would just reword your alternative hypothesis. All right, guys, that's everything for this section. In the next section, we will actually do some hypothesis tests with our calculator, so get ready for that, and I'll see you guys next time.